Hello and welcome to our group's presentation. My name's Casper and I'm going to do my section first, which is going to be about continued fractions. Before I continue, I'll just quickly explain what a continued fraction is. A continued fraction is an infinite fraction of the following form, where b0, b1, b2 and a1, a2, a3 are all integers. The way to work out what an infinite fraction is as follows. We write pi as a number and we split the number into the integer and the decimal, in this case 3 plus 0.14159265, etc, etc, etc. Then we rewrite the decimal part as 1 over the decimal, and then we evaluate the denominator, which in this case 1 over 1.41599265 is equal to 7.06251330, and then we repeat the process to the latest denominator. In this case it's the decimal starting with 7, so split it 7 plus 0.06251330, rewrite the decimal as 1 over the decimal, and then evaluate the denominator. In this case, the denominator is 15.99659, etc, etc, etc. This is significant, writing pi as a continued fraction. This is significant, pardon me, because you can create an infinite amount of approximations of pi, and here's how you do it. On the left, you've got a lot more iterations of the continued fraction for pi, and if we stop the continued fraction on the first fraction, what do I mean by this? Is if we just take 3 plus 1 over 7 and ignore the rest, and we evaluate it, we get 22 over 7, which is a fairly good approximation for pi, equal to 2 decimal places to pi. If we stop it on the second fraction, we get 3 plus 1 over 7 plus 1 over 15th, which is equal to 333 over 106, which is correct at pi to 4 decimal places. And if we do it to the third fraction, we get the following result of 355 over 113, which is correct to pi to 6 decimal places. And if you notice, the later we stop the continued fraction or cut off the continued fraction, the better the approximation we're going to get. And this works for any real number. And just to show, here it is 7 iterations. So if we stop the continued fraction after 7, on the 7th fraction of pi, pi would approximately be equal to 312,689 divided by 99,532, which is correct to pi to 9 decimal places. So in this way, by writing pi as a continued fraction and cutting it off at any step, you can create an infinite amount of approximations due to the definition of a continued fraction. Because the continued fraction is an infinite fraction, so there's an infinite amount of places you can cut off a fraction. So there's my section, and I'll carry over.
Leibniz formula for pi. The Leibniz formula for pi states the following. One simple well-known proof goes as follows. Therefore, obtain the arctan x series, where pi on 4 can be obtained by inserting x equals 1 into the series. The series was discovered by Leibniz, James Gregory, and an Indian mathematician in the 14th or 15th century, who is not known for certain but speculated to be a mathematician named Nilakantha. Leibniz and Gregory both obtained the arctan series in their study of infinite series before methods of algorithms and calculus were fully developed. Therefore, the arctan series played an important role in revealing early ideas of series and finding the area under a curve. Leibniz discovered the Leibniz formula for pi in 1673 when he applied the quadrature process to a circle using his method. Gregory was trying to find an infinite series representation of any function and discovered the relationship between this and the successive derivatives of the function, thus discovering the Taylor series, which can be used to prove Leibniz's formula. The Indian mathematician found the formula for pi on 4 by a direct rectification of an arc of a circle. Nilakantha's proof. He obtained the value of 1/8 of an arc of a circle, and he wrote it as a geometric series. He found this series at the bottom, where fn plus 1 is a rational function of n, which makes it a better approximation of pi on 4. And then the proof follows there, in the series at the bottom, where the idea was to choose an fn that makes the formula rapidly converging to obtain a more accurate approximation of pi, where Nellacantha uses this to obtain pi to 9 decimal places. Next is Viet's formula for pi, which states the following. It's the first recorded use for infinite product in mathematics, and was discovered by Viet in 1593, where he managed to work out pi to 9 decimal places. The proof for this formula was found more than a century later by Leonhard Euler. He showed that Viet's formula came from the iteration of the double angular formula for sine 2x, where the infinite product can be derived. It can also be rearranged, so it's pi equals. The formula produces two methods to produce a more accurate approximation of pi. That's equivalent to Archimedes' series, where that formula will have been multiplied by its conjugate and then simplified. And the geometric construction, which uses polygon's area in a circle, where the area tends towards pi. And if it's obtained by the Archimedes series, convergence goes as follows.
And we're going to be talking about the Ramanujan-Sato series and his approximations for pi. In total, Ramanujan had 17 approximations for pi, but I'm only going to talk about the two that interested me the most. One thing to note is that they were all published in a hypergeometric form, which you can see on the screen, and all of his approximations were proven by the Bauer brothers in 1987, quite some time after they were first published in 1914. The first approximation I'm showing you is often said to be his most accurate, as it correctly approximates pi to 8 decimal places, although it is worth pointing out that some approximations could go further than 8 decimal places, but they also became very inaccurate. For example, one approximation could produce 24 decimal places per term, but it wasn't correct up to 8 decimal places. This second approximation stands out to me because, in a way, it was quite far ahead of its time. It may initially look very complex in comparison to the previous approximation, but I'm also showing you the proof that was from 1987 as well. This approximation is special because it could calculate pi as well as 1 over pi squared. The problem with this approximation for 1 over pi squared is that it wasn't discovered until 1987 when the proof was released, as Ramanujan didn't realise that it could approximate 1 over pi squared. Another issue with this is, in 1987 we already had approximations for 1 over pi squared that were more accurate than the one from Ramanujan's equation, so it is a bit of a shame that its potential was wasted.
The Gauss-Legrand algorithm was created to compute the digits of pi. It is notable for being rapidly convergent by producing 45 million correct digits of pi with only 25 iterations. The method is based off the work of Carl Friedrich Gauss and Adrien Marie Legrand, combined with algorithms of multiplication and square roots. These are the equations you need to find the approximation of pi. Pi is then approximated using the equations as pi is approximately equal to a of n plus 1 plus b of n plus 1 all squared all over 4 times t of n plus 1. PiHex was a project organised by Colin Percival to calculate specific bits of pi. The software used for the project was made use of Ballard's formula, which was used over the BBP formula as it's about 1.5 times faster. Unlike most computations of pi, which give answers in normal decimal numbers, PiHex computed in binary because Ballard's formula can only be used to compute pi in binary. The total resources used for PiHex was 1,885 computers with 1.3 million CPU hours. The average computer would have taken 148 years to complete the calculations alone. In conclusion, we have produced information on all sorts of methods to approximate pi, and as we have shown, it has become more accurate over time.